Hello and welcome. In this video, we're going to talk about linear regression. Linear regression is one of the most popular techniques in predictive modeling. In fact, this is where it all begins. I'm sure this seems familiar. We know that if we are trying to find out a relationship between a dependent variable y with the help of an independent variable x, and there could be many examples of this. For example, you're trying to predict how much of a loan can be sanctioned to a customer depending on his credit rating. So the credit rating becomes the independent variable x, which determines the eligibility in terms of loan amount. For a student, we might want to check if we can predict the scores obtained in the exams basis average hours studied each day. Hours studied each day becomes your x, and the scores obtained in the exam becomes your y. There could be numerous examples of such relationships. Let's just understand what are we trying to do here. We are trying to draw a straight line which represents all these red points here. This line has a slope of beta 1 and an intercept of beta 0, which is the point where it is crossing the y-axis or intersecting the y-axis. We can simply put it in the form of the equation given on to the right. So let's say there is a value of y hat that's being predicted in terms of x, which is beta 0 plus beta 1 x. In this equation, we are giving importance to both the intercept and the slope. Now let's just have a look. What if we were to give importance to only one of these? So if we were to only consider the slope and not the intercept, there would be a possibility of drawing multiple lines which are parallel, right? That could be one way to represent it. And what if we were to only consider the intercept and not the slope? Again, in that case, we could have drawn multiple lines with varying slopes and the same intercept. So end of the day, if we were to conclude on one line, which is the line that fairly represents all these points, we have to concentrate on both slope as well as intercept. But there could be infinite combinations of slope and intercept. How do we decide which one to choose? And then there comes the ordinary least squares method. As discussed, this line is trying to represent these points. But not that all the points are necessarily fitting onto the line itself. They are some distance apart. So if you were to drop a perpendicular from each point onto the line, we can measure that distance. And what is that distance? That distance is nothing but a deviation. Deviation in terms of where the point stands, which is the observed value, versus the predicted value. That is also known as residual or error. So for each given x, this difference represents the distance of the point from the line. Now the question comes, how do we decide on the line? Now if you see, these distances could be positive as well as negative depending on whether the point is above or below the line. So for simplicity, we square this distance and we try to find out line in such a way that this minimum of squared distances, the sum of these squared distances all added up, is the minimum. And that becomes our regression line. Till the time you have just one variable, that is one x, that is trying to explain the y, we call it a simple linear regression. But the same concept can be extended to n variables. Y is being predicted not only with the help of one variable, but there are multiple variables. And often we'll be facing these situations in our real life scenario where a good outcome can be explained with the help of a number of independent variables, not just one variable alone. Let's discuss one of the most popular use cases of regression. It's about Moneyball, a book published in 2003 and a Hollywood movie released in 2011. This is based on a true story, and the story is about a team called Oakland A's, which once used to be a rich team, but it faced stringent budget cuts in 1995. Low budgets in sports implies inability to retain and attract star players. So any player who's in form would be charging a lot of money, but if your budgets are tight, you will not be able to afford that player in the first place. Now the interesting part which attracted the story for a book which became a bestseller and the movie which became a hit is, despite all this, the team Oakland A's continued to improve each year from 1997 to 2001. Imagine, with even tight budgets, they continued to perform and made it to the playoffs or finals from 2000 to 2003. Now, if you know and if you follow baseball, you would realize that it means a lot for a team to make it to the playoffs. And the best part was that they delivered a performance equivalent to the teams with 3 times higher budget. It's a story of belief, it's a story of intelligence, and it's a story of how you utilize the available assets to the best of your benefit. So let's just understand how this would have been made possible. The general manager of this team, Oakland A's, whose name was Billy Beans, engaged a Harvard graduate whose name was Paul DePodesta to assist him with this challenging task. While the things might seem a little easy to us now, because hindsight is always 20/20, things are not that easy when people are facing that challenge. And that's where this is a beautiful case of implementation of linear regression to solve a real-world problem. Level 1 starting point. First task before Paul DePodesta was to figure out the number of victories they need, that is the total number of wins. And basis the historical data, he found that there is a good linear relationship between the number of wins and run difference. In fact, run difference, which is a difference of runs scored minus runs allowed, could be a very good predictor of the number of wins. But now, how do we calculate runs scored and runs allowed? Again, there were second level of linear regression equations that were applied. So for example, runs scored could be predicted with the help of on-base percentage and slugging. And there is no need to worry if you're not familiar with these terms or these are jargons to you. End of the day, we are trying to understand how a problem can be solved in a step-by-step way using regression. Similarly, runs allowed could be very well predicted with the help of opponent's on-base percentage and opponent's slugging. Let's now look at the table as to what was predicted using the historical data versus what actually realized. So here's a comparison. Predictions made by Paul DePodesta claim that Oakland A's should be able to achieve or score between 800 to 820 runs, and they actually achieved 800 runs. Similarly, the runs allowed, Paul DePodesta estimated it to be between 650 to 670, and that was actually 653. Paul DePodesta had claimed that if we gain more than 95 victories, we might be able to make it to the playoffs. But with all the consideration that was given while forming the team basis these numbers, the team was actually able to achieve much more. In fact, they had 103 wins. This led to the emergence of a new stream of analytics in baseball that is known as sabermetrics. Oakland A's clearly had an edge for a period of almost 6 to 7 years when others started gradually catching up on this. But when they initiated it, they were the pioneers in this field to have introduced sabermetrics. Compare the performance of a team which is spending $30 million and is performing at par with the teams which are being paid almost $80 million to $90 million. So I believe in this case, the difference of $60 million that you see between two teams is something that's very well explained and compensated by the kind of intelligence that was put behind. A difference in the way of thinking. And that's beautiful about analytics because it kind of gives you that power where you make the right decisions using the data and you're not just making random guesses. Analytics is about being better than random, and this is a beautiful use case of that. Hope that motivates you a little bit. Let's move on to some discussion around a few terms which are important to understand. Coefficient of determination. It is also known as the R-square value, is an important measure of a model's performance. For a simple linear regression, this R-square is nothing but the square of the Pearson's correlation coefficient. The calculation, of course, becomes a little complicated as you move to multiple linear regression. Let's understand its interpretation. R-square value of 80% means that 80% of the variability in our dependent variable, that is the outcome of interest or the y value, can be explained by the independent variables considered in our model. While forming an equation in terms of a linear relationship of y with the given set of x's, you would have taken a lot of x's. Not necessarily all of them become important. So you are trying to understand if the x's that you've taken into account are able to sufficiently explain your y or your outcome of interest. So for example, if we were to consider the case of loan amount eligibility, the bank might want to consider multiple x's. It could be, of course, as discussed, your credit rating. It could be the kind of association that you have with the bank in terms of years. It could be the kind of balance that's carried forward each month in the account. What kind of other deposits you have with the bank, are those secured or not? and a lot of other factors like your age, your dependence, many more factors. Right, so a y could be best explained by a combination of x's, and of course these x's are not just randomly picked, these are recommended by the subject matter experts of that area. There are certain assumptions of linear regression. First of all, the relationship between the dependent variable and the independent variable should be linear and additive. So for example, in this case, when you plot these points, you see that probably there is a chance of fitting a straight line through it. On the other hand, if these points would have been like a curve, which is what you see here, it'll be like force-fitting a line unnecessarily. So whenever we have to work on regression, we will always see whether our x and y are associated linearly or not by plotting it. Second assumption is that the independent variables should not be correlated. That is, there should be no multicollinearity. That reminds me, in case you have not seen our video on correlations, please go ahead and watch that. I'm providing the link here. I think it will be a helpful source. Collinearity is the degree of association and the direction of association between the two variables. But we don't want to have x's in our model which are predicting each other. Because if your independent variables are related with each other, we are going to make a model which is redundant. So we want to add variables to our model which add value. Just as I talked about R square, when you add new variables, R square always goes up. But then there is another measure called adjusted R square that is there to keep a check on the number of variables. So we don't want to complicate our model. Trust me, that's the first thing in the mind of an analytics professional. He doesn't want to unnecessarily complicate the model. Because while you're working on any tool, to you it might seem as if, oh, we can add one more variable. But it's not just about the tool. When you commit to an independent variable x, you have to take measures to control it. So when you say that credit rating is an important predictor for the eligibility in terms of loan amount, the customer has to put an effort to ensure that he has a good credit rating. Likewise, for a business, if there is an outcome of interest and we associate it with an X or a predictor, we have to put measures to control that X. If we add unnecessary variables in our model, the R square will go up, but the adjusted R square will keep coming down. Next in the set of assumptions is about the constant variance. It's also known as homoscedasticity. So what we mean is that when we plot the residuals or the error, what is an error? The difference between the observed value and the predicted value on the regression line. So the residual should be constant with respect to the predicted values. As you can see in the first case onto the left, the values or the error is nearly constant. It's pretty close bound. But if you see onto the right, it's kind of forming a cone shape, which shows that the residual is not constant with respect to the predicted value. So this is one of the important assumptions of linear regression. And the last one is that the error terms must be normally distributed. So the error values, if you were to kind of analyze its properties, it should follow a kind of normal distribution. And I assume you've seen our video on normal distribution as well. I'm giving another link here just in case you've not seen it so far. It's very important. If you want to get a good grip of the subject, you must know normal distribution and some other common distributions. So we've done a video on normal distribution in the past that might be helpful for you. So now we've reached the end of this video. Hope you liked it. And if so, please give it a thumbs up and subscribe to our channel. Hit the bell icon so that you continue to receive our updates whenever we upload a new video. And the most important thing that I always emphasize, knowledge gets multiplied when you share it. So please share it with all those who might benefit. Thank you for watching.